All right. So first of all, thank you for having me here. It's always a pleasure to talk in any meetup that we have across Europe. Is really good. Um, so basically, I'm going to introduce myself, and then we dive into it straight away. So my name is Italo. I work at Lycon here in Berlin. I am CTO at Lycon. Previously, I worked in a few companies here in Berlin also, so N26 and HelloFresh. And then later on, I joined Lycon to basically grow a team from scratch and start diving into a different topic as well, a different industry. So the talk today is about designing for failure, and it's a topic that I am very passionate about. I really liked distributed systems. I really like the challenges that it brings to all of us. And that's why I like to talk about how can we design better software that is more resilient and it's able to fail gracefully whenever we have whatever fault into our system. So basically, I like to talk about designing for the unexpected. You never know exactly when something will fail, right? It's sort of a mystery. You hope things will work, but if they don't, how can your system actually behave better? So think about your systems today. Like, can they survive if, let's say, if an external dependency goes away, if your external API that you rely on goes away, can they still serve their customers, your customers? What if your database fails? What can you do about it? So if you never thought about any of these questions, this talk hopefully will bring some light into it. So we're going to go over a few topics today. So I'd like to talk about what is resilience, like a little bit of theory around it. And then we talk about latency controls, so strategies that we can use in our Go applications or whatever application, even if it's not Go, about latency control, isolation, self-healing, traffic control, observability, and then service meshes. So we're going to talk about all of these topics, and then hopefully in the end, you will have a little bit of more insights into these topics. Right. So what is resilience? I like to go a little bit back in history and talk about aviation. So I'm a huge aviation fan. If there is any aviation fan here, I'm glad to know. It's going to be nice. And basically, if you think about airplanes, right? So if you think about airplanes, last year, 2019, we had about 39 million flights going on across the world. That is a lot of flights, if you think about it. It's a huge number. Of course, this year, because pandemic, we had a very different, number overall. But last year, we still have like 39 million flights. That's a huge number. And out of those flights, unfortunately, we had 23 deadly crashes of commercial flights and private flights as well. And unfortunately, we had like 28 fatalities overall. But there are two flights which had a lot of more fatalities, which you're probably familiar with, which is the Boeing 737 MAX. And that flight was actually, it was actually disclosed by the FAA that basically was a software failure plus some other things in the report. But the software failure caused death of a bunch of people, right? And what is the point that I'm trying to make here? So I'm trying to say basically that aviation or software that goes in the airplane plus the electronic engineer that goes in the airplane was developed to fail. Every time you fly, like, worry not, for sure something already failed, you didn't know about it, and your plane landed safely. Because the planes are actually built to, handle failure successfully. One example that I can give you is a system called ELMS. So electrical load management system. So this system was created in 1991, and it was created by Boeing basically. And the whole principle of it is that you have a whole system that is electronically managed for, like if your batteries actually just fail for whatever reason in one side of the plane, you have a whole backup on the rest of the plane. So a few planes have like between 5 different batteries as backups. to 7 different batteries, just to ensure all the essentials are running. And the word that I want to make sure everybody understands here is the essentials. Can your software today actually live with the essentials only running? And that's exactly the question that we should make every time we develop some system and that we put it out there. So the airplanes, when I talk about essentials, we're talking about the FMS, so whatever the control system is, and all the hydraulic systems and so on and so forth. And in case all the batteries still fail, they still have another way of making sure that you still have enough power to actually land the flight successfully. So a little bit of like a little small fan comes out down from the airplane if everything fails, and then it generates mechanical energy, so you can still have or ensure that the essential mechanisms are still working. So that is pretty good. That is an interesting way, and I like to take this paradigm and then bring it to to software or to software development in the modern days. So I like this quote quite a lot. It's by Lian Guo. So resilience is a requirement and not a feature, right? So if you think about your sprint plannings, or if you run Kanban or whatever, if you think about it, do you put resilience as a first-class citizen in these discussions? If you're discussing, your technical requirements about a ticket, about a user story, do you think about resilience? Or do you leave it to later on, and then, whenever you need it, and then you start thinking about it? So I think Lian Guo here tried to make sure that we should not think as resilience as a feature that comes afterwards, but actually as a requirement for a feature to be done. So it should be in your acceptance criteria. So I really like this idea of trying to put resilience into the mindset of your product owners, your technical discussions with your tech leads, and so on. So that is pretty interesting. It's just a different perspective to help out the discussion flow naturally. All right. So latency control. So latency control is probably the most, let's say, the easiest way of actually trying to apply a little bit of safety around your software. So the first thing you should start with, whenever you develop a software, think about all the dependencies. So you have databases, you have external APIs, you have, if you have different instances, you probably have load balancing that you consider, client-side load balancing. So there's a bunch of things here and there that you have to think about. And latency control is a way for your software to actually control how much time it takes to go to an external dependency. So let's say how much time it takes to take you to Google. And the first thing I want to talk is timeouts. So timeouts are probably the easiest way you can ensure your external clients are covered. So simple way of creating a timeout in Go, right? Like easy way. It's creating an HTTP client. So you have an HTTP client right here. And you just simply say the timeout, right? Easy peasy. And then you create a timeout, you create a request. And this request comes with a context. And I'm going to explain why later on. So this is I think it was added in Go 1.14, not really sure. But basically comes with a context. And this is going to be useful later. So you create a client, you have a timeout, and then you create a client pointing to, in this case, just a mock API or whatever. And this API will actually, time out or delay the response for 3 seconds, and it will essentially fail. So whenever you do the do call, you actually get an error, and then it says, okay, the client timeout, and it didn't respond under 2 seconds, so I return an error. And then you're able to handle it, right? This is the easiest way, the simplest way of you doing so. If you don't do at least this on your external calls, or if you use the default HTTP transport or the default HTTP client even that Go provides, you should consider actually adding a timeout to that client or to whatever client. So this is the easy way. You can also just increase a little bit the detail of your timeouts. So, you can set the timeout overall of the whole transport. Or you can even go deeper and specify the transport layer. So you can have a dial, and then on the dial, you have a timeout of the specifically of the net dialer, and the keep alive time, and then the TLS handshake timeout, and you can go on and on and on. So I normally like to specify each of these timeouts. These timeouts are completely arbitrary, so please don't disregard the numbers. They should be adjusted to your own use case. Now, how do you know your own use case, and how do you know the magic number to put right there? So we're going to talk about observability in the very end, so that's going to help out. But basically, if you don't know, at all, you don't have any metrics going on in your system, I like to take the example from Nginx, which is a pretty well-known reverse proxy, which they have all these timeouts set in Nginx. So these are literally copies from it. So if you don't know anything, at least use something. So, right. So this is like going a little bit deeper. Now, we can also just, give better control when a timeout happens throughout your application. So before we go here, back here in this example, you had a timeout, an error happened. You're going to handle the error in this context, right? In this function context. And that's it, right? You can handle the error. You can just return the error and then handle it over in the upper layer. That's fine. If you want to be a little bit more flexible, you can use context with timeout, and then you can actually, enjoy the possibilities of context cancellation across your whole application. So that is useful in some scenarios. So you specify a simple HTTP client, and then you create a context with a timeout, provided your context, or if you don't have a context, just create a context background in the beginning. But I do recommend passing the context right here. And then, again, setting 2 seconds as a timeout. And then we created, again, the simple request to the same API. And whenever the do happens, these actually will, again, it will fail. You still get an error, but all the cancellation, or all this context that is propagated across your application will actually call the cancel callback, and then you can actually handle this. You can handle you can free up some resource in case you're using something. You can free up some database connections if you're using something, all across using the same context, right? So you probably want to do this in an upper layer even. So this way, at least you ensure that you can reuse this context, and whenever this call actually fails, this cancellation will be called, and then you can handle gracefully whatever other resource you want to free. Okay, client timeouts, that is easy for HTTP clients. And the same way works for, even if you go to layer 4, the same way is going to work on a TCP layer. And also, if you want to do, let's say, if you're using RabbitMQ, or if you're using Kafka, all of them, they have enough timeouts, and they have timeouts options that you should make sure that you are setting up. Cool. What about if you're building a web server, right? If you're building, let's say, very specifically, an HTTP server, you also want to make sure you protect yourself against long-running clients, against huge writing timeouts, or maybe you make sure that you actually avoid a leakage across your whole request response life cycle. So here, simple way of doing it. There is more complex ways of doing it. This kind of timeouts, but this is the simplest one that I found so far, and that I normally use. So again, basically, you just create a timeout handler, like simple handler that I have here as an example, and you create an HTTP server, and you set the read timeout and the write timeout. These are the very least ones. So the read timeout and the write timeout, and then you have the idle timeout, read header timeout, and that's pretty much it, right? So you set these 4 things, and you already make sure that your server is a little bit more protected against external calls or low-hanging fruits that you have there that is taking up all of your resource or your timeout sockets. Your request sockets and so on. So you want to make sure that you set some timeouts on your server. Right. So client timeouts, server timeouts are great for HTTP and TCP and whatever kind of RPC connections you have. And you can also set, as I said, on Kafka, on RabbitMQ, or whatever other event broker or message broker you have. But we can go even a step further, right? We can go even a step further. So we can have circuit breakers. So circuit breakers, they work exactly as they're supposed to. Like if you have a house and you have a house with some electric energy going on, you definitely have a circuit breaker somewhere in your place or in your building. And like what happens is that if you have a circuit actually just like getting all destroyed, the circuit breaker actually opens, and then it avoids the whole wire actually getting on fire or endanger your life. So the circuit breakers were created for controlling where the energy flows across your whole wiring network. So it was pretty smart. And we can also do the same in software again, right? Because if you think about it, your whole software system, if you work in a distributed system environment, and I'm pretty sure you do, even if you don't realize it, you have a few dependencies, as I said before. And those dependencies are your wires. And calls to those dependencies are exactly the wiring going up and down across your whole network. So your whole service mesh. And a good way of protecting, let's say, upstream calls is actually enabling circuit breakers. So in Go, there is a bunch of libraries for doing circuit breaker. You can build your own, although I do not recommend it because you don't want to reinvent the wheel. So I found out one that I like personally, very, very good one, is Go Breaker, and it's basically from Sony. So they have created this interesting library, which is easy to configure. So you create a secret breaker, you name it. So let's say that I'm calling Google. So I name it here. Okay, I'm going to name HTTP GET example, and then I have a little bit of a round trip rule, basically. So whenever the call goes to Google and it fails, so round trip is complete and then it fails, and it fails more than 3 times, and the failure ratio is actually bigger equals than 0.6, I actually want to trip the circuit, right? So if it fails 3 times, I basically just want to say, hey, stop calling Google for a while because they are failing. That's very unlikely, but stop calling Google because they're failing. And now, you eventually will try to call it back again. But the utmost goal here is just like, stop calling Google. And without human interference, right? So we want to make sure the circuit breaker will open. So whatever code is in here is not going to be executed if Google fails 3 times or the failure rate reaches 0.6. So here I'm just normal HTTP GET, calling it, boom. And then if the status code is actually a bad request, then I return it. I return an error and say, hey, something's wrong. And then this will get into action and start recording it. Start recording the counts, right? The request count. And then another client will try to do it again and again, and then it fails and it fails, and then boom, and then you open the circuit. Once the circuit is open, you cannot do much, right? Then you're completely out of communication with Google, which is what you want, because you don't want to overload the upstream server, in this case, Google. So you don't want to overload and keep calling it if the upstream server can't actually handle all the requests. So that is the whole point of circuit breaking. Now, you can even go a little bit ahead. If there is any Java developer here or Java people that actually develop in the past, you probably heard about Histrix. Histrix was a pattern developed by Netflix a while ago. It was a great pattern. Right now it's deprecated, but I still like to show the whole essence of this pattern. So basically, Histrix was a very, for a lack of a better name, they call it the fat clients. This term is probably like complicated these days, but it was used to be called like that. And because the clients, they had all the necessary decisions for being resilient. So if you're going to call an external dependency, basically that client would have circuit breaking, would have retries, it would do load balancing for you, it would do service discovery, and then client side load balancing, and so on and so forth. So that's why it was a so powerful client. This pattern today is being changed by something else, and is the reason why I like to talk in the end of this talk about service meshes. So this pattern is evolved, I think, in the last 2 years now. It's evolving more and more and more towards service mesh. But there is a lot of people, and there was a lot of value in this sort of clients. And Histrix was one of the probably the most interesting creations out of this whole Histrix client. Through this powerful client. So Histrix was a way for you to like have all of that in and circuit breaking. So here's the dashboard that was used to be shown when you had circuit breaking. So, you can just see each of your external dependencies, the amount of calls. You can see if one of the circuits is open or closed. You probably want everything closed and working. But if one is open, you see it right away. Now, Histrix is deprecated in favor of Resilience for J, if you are on Java, but and some other possibilities as service meshes, as I mentioned before. But you still can have a nice dashboard like this, even working with Go Breaker, right? So you can just attach a little bit of a Prometheus counter here, and then you have a wonderful counter. You can build your own dashboard. There is a bunch of open source dashboards for circuit breaking for Prometheus, so you can just copy and paste literally and ensure the metrics are flowing in there. If you don't have Prometheus, if you use StatsD to, GoDog or whatever, you can do the same. So it works really well. And so this is Histrix. Circuit breaking is very powerful and very nice. But if you noticed, I mentioned before that, okay, we open the connection here because Google failed 3 times. And you might wonder, when will the connection close again? And I can say to you, if you only have circuit breaking, it won't really close. It will remain open until you reset the server. Now, what you can do is add retries. And now the whole thing kind of, comes together and you have a whole different automation. You barely need to touch it. So basically you have a consumer service. So someone that is calling some other service. And you want to make sure you wrap your external call around the circuit breaker, and you definitely try to add some retries. So let's say that I'm going to do the same call over to Google over the circuit breaking and the retrier. So this request will go through the circuit breaker. Circuit breaker will then call Google using a retry mechanism. And this retry, you can say any kind of rule for it, right? So you can say, please retry 3 times. And then if it fails 3 times, then the circuit breaker opens. So in theory, we're going to have like 9 different calls until the circuit breaker actually opens, right? So the retry is actually going to ensure, because sometimes you just have a network hiccup because of whatever reason. So you just want to make sure you retry. The problem is that you don't want to retry right away. You want to retry in a specific time difference. So here's an example of this. This library is created from Avast. It's a retry Go, really nice, really easy to use. You can write your own, of course, or you can just look it up. But this one is the one that I like the most. So again, all over the place, we just want to make sure that we wrap it around it. So we have a HTTP GET, we have a URL, and then you have a response, and you do whatever with it. And then here we have a retry attempt. So I said 3 times. I want to make sure I retry 3 times. And the delay type, and this is the most important thing. The delay type, you can have multiple kinds of delay, right? You can have linear delay, which means, okay, every time the API fails, retry every 2 seconds again. So call, fail, wait for 2 seconds, call, fail, wait for 2 seconds, call, fail, and then wait for 2 seconds. And until it reaches the threshold of 3 attempts. That is a linear approach. But if you think about an external API, it's very unlikely, unless if it was a hiccup, it's very unlikely that the external API will just come up alive once again after 6 seconds. So, or six, or even more. So you want to make sure you have an exponential delay. So whenever you call this, you have an exponential growth. So, okay, 2 seconds for after the first fail, now 4 seconds after the second fail, and then 8 seconds, and so on. So you multiply. So it's exponential growth of your time of retries. And these values have to be very sensitive here and there. And even though, like, if the whole thing actually fails, then you want to make sure you open the circuit. Otherwise, you're going to overflow the whole upstream. And then you have a bigger problem of cascading failure, which we're going to talk about in a few minutes. All right. So again, timeouts, circuit breakers, retries, those are probably easy ways for you to add to your software today. And right now, just have out of the box better reliability across your external dependencies. The biggest challenge you're going to have is actually identifying your external dependencies, like which ones are worth to invest this time to add a retry, to add a circuit breaker, and to add some timeouts. But then we go into another topic, and we go into the topic of isolation. So, like, if you have your external dependencies mapped out, and if you have added your circuit breakers and your retries and your timeouts, it's great. But that is protecting other APIs from actually, aside from the timeout from the server, it's protecting other APIs from being overloaded from your own call. And you want to make sure you can free up some resource from your calls to be used somewhere else. So there is a pattern of bookheads, which is an interesting pattern. That was mainly, bookheads come from way, back in history from the naval industry. So if you ever saw Titanic, and the Titanic was actually an interesting way of analyzing bookheads. So if you look at this GIF right here, the Titanic hit an iceberg, and this iceberg basically cracked the whole shelf of the ship. And then this yellow lines right here are bulkheads. So the Titanic sank because essentially all the bulkheads were full of water, and it was too heavy to actually hold the load. And then it broke in the middle, and then it went down. So the interesting thing to notice here, the Titanic had a design failure. If you read the documents in the internet, even if you watch the movie, the architect says there was a design failure. The bulkheads, they were actually, they were actually created to contain something. They have to contain water or to contain fire, and to make sure it doesn't spread across the other bulkheads or the other rooms. So if you remember the movie, whenever the water was filling up one compartment, there was a huge door which closed automatically, and then tried to contain the water. That was a bulkhead actually on action. But of course, it didn't work. And the reason why it didn't work is because there was a little bit more water than you can actually hold on to each bulkhead. So the bulkhead had a water. Had like a space on the top of the bulkhead which allow air through, so people could breathe. The problem is that where air passes, water also passes. So the water was going up and then passing over to the next bulkhead and the next bulkhead, and so on and so forth. If we only had 4 compartments being completely overflown, that would be okay. But you can see here in the GIF that it starts going to the 5th compartment, and then it breaks exactly in the middle because it was too heavy, and because there was a design failure in the whole bulkhead system. So I'd like to compare this and put this into software again. So bulkheads, and what you should remember is bulkheads is supposed to contain failure, right? Fire or gas leakage or water leakage or whatever fluid, anything. Bulkheads are supposed to contain something. And in the naval industry, that's super easy. In software, it's hard to actually see that happening, but they do happen. So there is a library called Heimdall, which is, again, it's a powerful client strategy, right? It has circuit breaker in already configured. it has retries, and it also uses bulkhead. So how do we use bulkhead in Go or in whatever language? Essentially, what you want to try to do is that you have a thread pool or a Go routine pool, and each external call that you're making are actually being allocated in a single Go routine. You want to make sure that you don't call on the main thread or in the main Go routine that is running your code. Because if you do so, and if that request fails or hangs for whatever reason, your main Go routine is going to hang, right? It's as simple as that. So you want to make sure that every request that it's being executed are being distributed across the sync pool, or this Go pool, Go routine pool, and being called to the external server. If one call fails or hangs, only one Go routine will be failing, and then you can handle that separately. The other Go routines will still be completed, hopefully, if the server is just misfunctioning one of the nodes or whatever. The other Go routines can still be load balanced to different nodes, and they can still work, so your application doesn't block. This is a simple concept that I never thought about, and probably some of you already never thought about it, but it's super smart, right? Because then you distribute it across different Go routines, and boom, there you have it. You're a little bit safer in the external calls, and that's exactly what you want to make sure it happens. So if you use a library like Heimdall, it does that for you. So it has a pool of Go routines that can be distributed across different external calls, and if one fails, don't worry, other calls are still going to make it, and your application is still going to work. You can build that yourself again. You can build the Go routines pool and then manage that, or just use a library like this. So in Java is the same. Resilience for J uses bulkheads. If you like this, there's going to be a link at the end, which is from a paper from Microsoft, where they explain how this works in C#, and it's really great. It's really nice to read about it. And this one is implemented in Go, in Heimdall. So if you want to check it out, just go to the library and check it out. It's really nice. Okay, so let's say that everything is failing, and you've implemented all possible solutions for minimizing your failure in your service, so you can still serve traffic to your users for the essentials. But how you make sure that your application try to heal again by herself, and you want to make sure that you don't want to wake up in the middle of the night just because a node went down, right? Or one of your instances went down. So for that, you need some groundwork to do. And the groundwork, especially here, is health checks. So you want to make sure that your application has health checks. Today, if you're working with any applications in the web, especially APIs or anything like that, if they do not have a health check, go add a health check right away. That's the best thing you're going to do for your application. Because I'm going to show you this is going to be used by some other applications to actually, make sure your application is alive, and then it can do something. You can restart your node, you can, redeploy, auto-scale, whatever. So this library here called Health Check, this one is actually specifically for Kubernetes, but it works well, and I tested with Nginx as well. So works okay, or HA proxy if you use any kind of reverse proxy. So here, what you want to do is actually you create a health check, you add a liveness check, and you add a readiness check. So the liveness check is a check that Kubernetes does to make sure your application, while is running, is not performing badly, right? So here is just, again, an arbitrary number. I put it 100 Go routines, count check, but it can be whatever. There are many built-in liveness check that you can choose from. But here I'm just checking, hey, if I have more than 100 Go routines running in this application, something is off. Something is not right. And then we have readiness checks. And these readiness checks are let's say, the hard dependencies of your application. your application cannot work if these are not up, right? So database, payment services, Google, for whatever reason. So these ones, if they're not up, whenever Kubernetes is scheduling your pod to go up, it will wait until these are actually returning okay. And if it's returning okay, then Kubernetes schedules your pod to actually go and, okay, it's ready to run, good to go. Especially when you have a deployment strategy, like, rolling updates or stuff like that. You want to make, like, Kubernetes will make sure that the readiness checks are passing, sorry. And again, the liveness check is something like, okay, if it's not behaving really well, then Kubernetes will flag it and will say, hey, this node or this instance, this pod is not behaving well. I'm going to try to restart it and I'm going to do something else. But I'm not going to force it, so it doesn't drop any connections. So this goes too much into Kubernetes. But regardless of the underlying scheduler you have, or if you don't have a scheduler, if you're putting up the server by your hand, like by yourself, you still have a load balancer probably somewhere. And if you do, that load balancer, they can check if your application is healthy and running. And if it's healthy, you want to make sure you just put it in a different port, because you don't want to block the port that you're using for HTTP connections of your application. So you put it in a different port, check it out, and make sure you have a health check. So normally you can just check the health check. In this case, I just do localhost 9090/live. This foo is totally optional. It's just because it says, oh, hey, your Go routine threshold is okay. And then it returns 200. Same thing for the readiness. Hey, Google, Go routine threshold and the payment service are actually up. So 200. If anything fails for the ready check, it will say, hey, example.io, I couldn't find this host. So 503. And this 503 is then used by Kubernetes or by Nginx or by HAProxy to flag your host is unhealthy and to make sure that it doesn't schedule anything else in there. So it's super useful. And this way, it will flag it to restart or to retry, and then your application restarts automatically, which sometimes, Bill Gates just restart it just works. And that's unfortunately true. Sometimes, for whatever reason, you just restart and it works. All right. Then jumping into a topic that is not very famous, that is basically Outboxer. So the Outboxer is a pattern which is super interesting about like how you can make sure that your application, if something fails, you want to make sure you have a queue, and in that queue, everything works really well. So basically, let's say that you have an external call, that you put a message on Kafka or into AMPQ, so RabbitMQ, and RabbitMQ is not there, but your message should still be stored somewhere, and then it goes into your primary storage, which in this case is Postgres. And then basically all you do, you configure an Outboxer with a data store and then an AMPQ server, a little bit of intervals, and then this library will make sure that whenever RabbitMQ is not available, I will store the message into Postgres, and whenever RabbitMQ is back up, I will take the messages that is stored in Postgres and then we'll publish into the RabbitMQ once again, automatically. There is a debate about, hey, RabbitMQ should never fail, or Kafka should never fail your clusters. And what if your database fails? And then you're like, well, then you have a bigger problem, right? If your database fails, that's a hard constraint, then you have a bigger problem. So this is just a way of storing this transaction so it doesn't go out of hands, basically. All right. How are we on time? Okay. Just have to hurry a little bit. So the Outboxer, simple like this. Again, we put it in an Outbox record, and then in there we'll make sure that whenever AMPQ is not available, it will retry for you. If you want to check it out, This library was created by me, so just check it out if you like. There is a paper again from Microsoft about Outboxer. I will leave the links back in the links channel in the slides. So traffic control, very quick. We have rate limiters, and rate limiters are probably the easiest way of limiting traffic coming from outside to your API. So we have, essentially we have rate limiters. This library is from Ulule. Simple, like you have a rate limiter in memory storage. And this is great when you have a single instance of your application running. But when you have multiple instances, what you want to do is actually have a load balancer. So you want to make sure that you have a load balancer, sorry, not a load balancer, a distributed rate limiting working with load balancers, because then if you have requests coming from node 1 or node 2, it's actually counting on a storage, a distributed storage, and then it makes sure that the rate limiters are equal across all instances. Super useful. If you want to check it out, there is this like nice blog explaining how distributed tracing works, distributing rate limiters works. So it's really, really nice. And here's the library. Back again, the same library, but now I configure Redis, and then I have a Redis store. And it works just like that. So it's simple, it's nice and easy. All right, last topic is observability. So we have a little bit of metrics here. Nothing that I said before is useful if you do not know how your service is behaving. So metrics is essential. So if you don't have metrics today in your application, please go ahead and try the best that you can to add some metrics. So Prometheus is my favorite one, but you can choose Godog, Honeycomb, whatever you like, even New Relic. So you can try whatever with the agents and etc. But have some insights of what's happening in your application. So metrics are essential here. Distributed tracing, I won't say it's essential, but it's a great and nice to have. Like if you have a tracing, stating exactly what's happening in your request flow, it's going to help you a lot. And for tracing, I like to use the OpenCensus library, which is great because then you can just change the exporter. If you don't like Jaeger, you want Zipkin, you can just change the exporter and your whole code remains the same. So this is really nice library. This is OpenCensus, this is Open Tracing, and they're combining forces with OpenTelemetry. So this is coming soon, it's in beta right now. Check it out. This is a wonderful project from a lot of smart people, and it's really, really great about how they're doing this. So that is a lot of things, and Service Mesh comes into place. So Service Mesh, basically Istio plus Kubernetes is what I like. I'm just rushing up here because of time. But basically the Service Mesh architecture that I mentioned is the counterpart of the heavy clients that we have. And then, you can configure all of the things that I mentioned before in the code, you can configure it in the infrastructure layer. So the sidecar that runs across or side by side of your application is going to take care of timeouts, retries, and circuit breaking, and a bunch of other things. So you have retries capabilities, you have timeouts capabilities, and a bunch of other things. Circuit breaking, as I mentioned. So this is the circuit breaking configuration. So there is a lot of interesting things that you can use the Service Mesh for. But again, Service Meshes are very complex. If you don't need it, don't use it straight away, out of the box. But if you're working in a microservice environment, you probably want to consider using it. Or if you're working with a lot of services or even monolith, like a lot of them, you probably want to put it in your mesh. So it's easier to solve service discovery, client-side load balancing, circuit breaking without touching your code, literally out of the box. Yeah, exactly. So here is how basically we create these codes and all these configuration files into our, I use Terraform to create GitHub projects, and it comes with a bunch of interesting things. All of these are going to be listed out in the links down in the end. So a recap, we talked about what is resilience, talk about latency control, timeouts, circuit breakers, retries, bulkheads, health checks, Outboxer, rate limiters, observabilities, and very fast about Service Mesh. So yeah, I hope you can use one of these, strategies in your services starting today. if you actually never had one of those. And if you know these topics, I hope this was just a little bit of a refresher. So please, if you want to check it out, my talk, it's on GitHub, italolelis/talks. If you want to check it out on an application using some of these patterns, Coffee Shop, because I love coffee. Here is the link for the Microsoft that I mentioned. And please follow me on Twitter if you want to hear a little bit about resilience. And I really want to thank you all for the time. I'm sorry that I ran over a little bit of the board. So thank you very much.